Have you ever tried lighting a sodium lamp and wondered why sodium glows so easily? That's because it readily gives up its electrons, and that brings us to an important periodic property, ionization potential. Ionization potential, also called ionization energy, is the amount of energy required to remove a loosely bound electron from the outermost shell of an isolated gaseous atom. For example, when we remove the first electron from an atom M, the reaction is M gives M++ electron. This is called the first ionization potential. If we remove a second electron from the already positive M+ ion, it becomes this is the second ionization potential, and it's always higher than the first. Ionization potential is measured in electron volts, abbreviated as EV, which is a unit of energy. Now, let's break down what really influences ionization potential. First up, atomic size. When the atomic radius increases, the outermost electrons are farther from the nucleus and hence experience less attraction. So, they are easier to remove, which means ionization potential decreases. Next, we consider the nuclear charge, the number of protons in the nucleus. A higher nuclear charge results in a stronger pull on the electrons, holding them more tightly. This makes the electrons harder to remove, so ionization potential increases. Also, remember the role of inner shells. They create what we call the shielding effect, partially cancelling the nuclear pull on outer electrons. This shielding makes ionization easier, reducing IP. Balance of factors. Ionization potential is determined by how tightly the outermost electron is attracted to the nucleus. So what happens when we move across a period from left to right in the periodic table? Two main things occur. Atomic size decreases because the number of protons increases but electrons are added to the same shell. This shrinks the atom slightly. Nuclear charge increases, pulling electrons more strongly toward the nucleus. Together, these two factors make it harder to remove an electron, so ionization potential increases across a period. In period 2, ionization energy increases across the period. Lithium is 5.4 electron volts, carbon is 11.2 electron volts, fluorine is 17.4 electron volts, and neon is 21.4 electron volts. Now let's move down a group, say group 1, the alkali metals. As we move downward, atomic radius increases due to the addition of new electron shells. Shielding effect becomes stronger, reducing the effective nuclear attraction on outermost electrons. So what's the result? It becomes easier to remove electrons and hence ionization potential decreases. Take a look. In group 1, ionization energy decreases down the group. Lithium is 5.4 electron volts, sodium is 5.1 electron volts, potassium is 4.3 electron volts, and cesium is 3.9 electron volts. Let's now talk about some interesting comparisons. Helium, despite being at the top of the table, has the highest ionization potential of all elements. Why? Because it has a very small atomic radius and a tightly packed nucleus, electrons are extremely well held. On the other hand, cesium, with its large atomic size and single valence electron far from the nucleus, has one of the lowest ionization potentials. That's why alkali metals are so reactive, they lose electrons easily. In contrast, noble gases rarely react, they hold on tightly to their electrons. And here's the rule of thumb. Metals have low ionization potentials, they're good at giving up electrons. Nonmetals, especially on the right side of the periodic table, have high ionization potentials, they prefer to gain electrons. Application. Ionization energy explains reactivity trends. Elements like sodium react easily due to low ionization energy, while helium remains inert because of its very high ionization energy. So let's quickly revise what we've learned about ionization potential. Ionization potential is the energy required to remove the outermost electron from a gaseous atom. It increases across a period due to decreasing atomic size and increasing nuclear charge. It decreases down a group due to increasing atomic size and greater shielding effect. Noble gases have high IP and are chemically inert. Alkali metals have low IP and are highly reactive. This property helps us understand and predict the reactivity of elements.